Okay, so I'm Bryn Phillips from the University of Oxford, talking today about instrumentation and monitoring of a concrete jacking pipe. So this is a pilot study that we did for a further body of work that's forming a PhD for me, and is forming under Bryn, who's in the audience, his work with his European research grant. So an outline of what I'm going to talk through today. The project is a pipe jacking project, so I'm just going to very briefly go through what that is for those of you who may not be aware. And then introduce the pilot drive, and then just quickly go through some of the data that we got from the drive itself. So pipe jacking as a whole, it's a trenchless installation method. It's kind of a scaled down version for the most part of kind of the larger things that we've seen from Tideway and from London Underground. It's more analogous to kind of drilling offshore, in that essentially what you have is we have this sort of shaft or pit that's constructed at the launch and the reception side, into which you drop a jacking frame, which provides all of the thrust that we need to push a pipe string with a tunnel boring machine on the front of it through the ground. So the tunnel boring machine itself has, in red here, you can see a head which has a slightly larger diameter than the pipes that follow behind, and the idea is that that creates an annular gap or an annulus around the pipes, which is then filled with a lubricant to reduce this force S, which is the skin friction force between the soil and the pipes, which ultimately, especially in long drives, leads to increased costs and affects the feasibility of drives over a certain length. So what you can see here on the right is just an example of this setup from one of Wardenberg's drives in Canada at the bottom of a concrete shaft. So you have the jacking frame in yellow here, a little launch seal here on the wall to stop any water or soil coming back into the shaft, and then the TBM there just about to go out through the wall. So if we go on to the motivation for the research, so there's sort of three areas that we're looking at and trying to assess in better detail. So contact stresses, these are what I was talking about earlier in terms of the stresses between the outside of the pipe and the soil, so trying to better define that soil structural interaction. Currently, there's a lot of work that's been done theoretically on modeling with this, but there's been very little direct measurement, no real direct measurement at this scale done on any actual drives. We're then looking at lubrication behavior. So these lubricants are obviously key for the drives, for their success. And there's been a lot of work again done in the labs, but there's been less done on sort of time-dependent properties and also how these lubricants actually perform in practice. And the final area we're looking at is pipe performance, which is how these pipes respond to the loads during installation, so the temporary and the transient loads, and then finally, potentially in the future, looking forward to do structural health monitoring of these pipes as well. So the two research tools that we're kind of using for this at the moment are field monitoring of tunnel drives, which is what this presentation and paper was about, and then obviously laboratory and scale testing, which is something that we're looking to develop more in the future. Via some nice tunneling then, we will hopefully have outputs of improved or better validated design methods, and then new monitoring methods we're hoping to develop as well. So the pilot drive itself was up in the Lake District, happened from the 5th of September to the 5th of December last year, so it took 3 months to complete, and it was a 1,237 metre, or 1,241, depending on who you ask, tunnel drive, 2.2 metres internal diameter, 2.75 metre external diameter, constructed, as I say, underneath this hill, essentially to avoid a diversion that came all the way around here and avoided a lot of unstable ground around the A66 on the way into Keswick there, up in the Lake District. The drive itself, this hill, had a maximum cover of about 60 metres, a hydrostatic head, we think, within the ground of about 2.5 to 4 bar as we went through it, and it was all through a very low abrasivity, very consistent mudstone, so it was fairly ideal conditions for driving the tunnel. So the instrumented pipe section that we produced, here's a little schematic of it. We had the 4 sensors on the outside, shown here in orange, and what they were is electrical load cells, which I'll talk about in a bit more detail in a second, and also pressure transducers so that we could separate out pore water pressures from the total normal stresses that we're seeing on the pipe. And then within the pipe wall, at the 4 kind of corners as well, we had electrical vibrating wire strain gauges installed to measure the axial, the hoop, and the kind of 45-degree strains that are observed in the pipes. And because we were specifically interested in the hoop strains for this project, we also had 4 additional sensors in at the quarter pipes points, just measuring the hoop stresses. So you can see here, it's not the clearest photo in the world. It's quite hard to take photos inside rebar. The phone cameras and cameras don't seem to like it. But you can see at the top here, this is the strain rosette. So there's the axial, horizontal, and a 45-degree sensor. And then below here, hiding on the outside, is the pressure transducer and electrical load cell. So these electrical load cells themselves, they were 3-axis electrically gauged load cells, which we tried to seal as best we could before casting in with a silicon sealant. And then just poking over the top of it here, you can see the pore pressure transducer, which had a filter cap on it to make sure that they remain saturated throughout the transport and casting process of the before the pipe went to site. So this was the pipe being dropped in on the left and installed on the right. So we have obviously a data logger housing, a UPS housing, and it connected into this lighting circuit, which was handily at 110 volts, that runs all the way up the tunnel. And you have to see everything we have to avoid within the tunnel. So there's additional services for the slurry that transports the excavated material from the head of the TBM back to the ground. There's then sort of additional communication cables. This red cable was a 10 kilovolt power cable, so we're quite keen to be on the other side to that. Be a little bit worried about electrical interference from that, but we think for the most part that didn't have any effect on the results we got. So if we look at firstly the axial loads that were measured here, I'll just explain through this graph. These kind of fairly consistent dark grey dots at the bottom are the force on the head, so that was that kind of face resistance R here. The grey line that's increasing with the length of the tunnel across this x-axis is the total force that's from the jacking frame at the back here. And then this kind of black, fairly scattered line is the axial force that we recorded in the instrumented pipe itself. So what we found is, I guess the reason I put this one up is it's quite interesting, is that you would expect that as this section here got longer, so as more pipes were put in behind, as the whole drive got longer, you'd expect to see more of the skin friction coming from that section. So this bit in front is a fixed length. This is getting longer. You would expect to see that section increasing in friction. What we actually see, if you compare from, say, 900 meters here to 1,000 meters here, is at 900 meters, the force that's on the pipe is very similar to the jacking force, or is kind of up near the jacking force. So that means a lot of the friction is coming from the front, and there's very little from the back section of the drive. Whereas at 1,000 meters, you see it's right down here, kind of closer again to the resistance actually on the head of the machine. So what that means is that most of the resistance is no longer coming from the front and more of it's coming from the back section there. If we dive down into that data a little bit and have a look across the axis of the pipe, so we have the top graph here being the north sensor versus the south sensor for the chainage of the instrumented pipe section, and then east versus west. There's quite a clear coupling you can see across the axis, so that when the north sensor here goes into compression, which is downwards on these graphs, you see that the south sensor here goes into tension, and that tension is fairly significant at just under 50 microstrain. That equated, we think, to a maximum tensile stress of about 2.3 MPa in the concrete, which is a significant portion of the concrete's actual tensile capacity. So that's what we're saying there. So there's a few examples kind of highlighted of where this happens across both axes. This is especially interesting considering that this drive was completed straight with fairly minor steering corrections at a constant grade. So if there was a curved drive where you would expect all of the load to be going through the inside of the bend as you go around it, this would potentially be much more severe, and that tensile stress in the concrete could be a concern. And this is something that isn't really considered in the standards for tunnel and pipe design at the moment. So now if we move on to the external pressures and the hoop strains that were recorded, this first part of the plot here is the external pore pressure in kPa. And you see as we went deeper under the hill, that increased and then kind of stabilized, and there was quite a lot of variance in it due to various practical factors with the tunneling on site. If we compare that to the average hoop strain, so that's the hoop strain of all of the 8 sensors averaged, you see kind of as you'd expect, as the external pressure increases, this hoop strain increases as well, and the pipe goes more and more into compression in the hoop direction. Now we're going to specifically look at this section sort of 250 to 300 meters. So you can see again that quite nice coupling where there's a spike in the pressure here. There's a spike in the hoop strain as well going downwards there. So that's quite nice to see that the data is matching up. So what this plot here now is for this sort of 260 to 300 meter section. It's a little video that's going to play through hopefully. And this left-hand plot shows the overall hoop strains, and this right-hand plot will show the bending strain, as we called it, which is the measured strain minus the average strain throughout the whole ring, is how we've defined that for purposes of this. There's two things I want to pay attention to on this. In the left-hand plot, it's quite interesting to see the amount of variance and how quickly it happens in the pressures. And on the right-hand plot, see if you can see any difference in the performance of the pipe around the whole perimeter. And that's not going to play, which is annoying. Go on. See if it'll... Hey. Okay, so that's not going to work, but oh well. So what this plot shows essentially is that as the pipe progresses through this kind of 30-meter section, there's quite major changes from about 50 microstrain to sort of 150, which we've seen from the previous plot to do with the pressures outside. But also of interest is this point here actually goes into quite a lot of compressive strain compared to the rest of the ring, and then it goes out again. So what that's showing us is that we've passed some sort of a bump or some kind of a protrusion into our annulus that's putting a force on the pipe wall that again isn't necessarily accounted for in design. And that was actually using about 25% of the capacity of the bending moment of the wall, the bending moment capacity of the wall rather. So if we move on now just to talk about the contact stresses, so these were the externally mounted sensors. You'll notice the scale at the bottom here only goes for the first 70 meters, so that might be an indication of how well this went. If I draw your attention to this is the pore pressure versus the normal stress. So you see the pore pressures, as I've shown you, kind of increase as we go up in the drive, and you notice for this, say, north sensor here, the normal stresses recorded actually begin to go down. Now what we believe that is water penetrating around behind the face of the load cell and into the back of it, so that we're not experiencing this pore pressure. And what I haven't shown you is at about 90 to 100 meters, each of the circuits in the load cells begins shorting out and firing from maximum to minimum to maximum to minimum, which is less than ideal. Let's just highlighting that. So I guess in kind of a summary of what I've just whizzed through there, installed the instrumented pipe section. The skin friction was varying by quite a large degree, which is something that we found very interesting. The axial strains, even though it was a straight pipe drive, were not evenly distributed around the pipe walls and also varied, and the sections of the pipe wall going into tension. Again, the video that didn't work, bending moments in the pipe wall within what should have been a stable bore, so you'd expect it to be kind of a more smooth circle. The high pressures generated by the lubrication process as well. And the electrical sensing on the outside of the pipe is not robust enough for this kind of measurement technique. We've had success in it for measuring shaft sinking in the past, but we think this is a much more hostile environment. So what that's kind of leading us onto, and also will build for the future kind of lifetime monitoring of the drive, is to look at trying deploying fiber optic sensors, both as load cells, which is in development, and as FPG gratings into the pipes themselves. So at that point, I want to say thank you, and if anyone has any questions, this is again supposed to be another little time-lapse video, but oh well. So does anyone have any questions there?